the only the weights of network 2 will be updated. Okay, that is how you can make sense of it. I have given you one Stanford course. Okay, now there, go to the course notes, and then there you can see some of the topics where in which he explains backpropagation. So where he takes a sigmoid node explicitly, he takes a specific sigmoid node, and then he explains how to do the backpropagation. Okay, to
It's
that
in the
specific
course
sigmoid
notes.
node. It's in the course notes of the link that I have given.
Okay, we'll check that
Now,
out.
this is one of the very good resources on CNNs. Okay, now they have really given a very good resource on CNNs. Now, to understand CNN, now this is one of the best resource that I have come across. I'm not saying that there might be some other good resources, but this is one of the notes that I have come across. And apart from that, one other resource that I have come across is Three Blue One Brown channel. Everybody knows Three Blue One Brown.
Yeah, at least I'm aware.
Uh, yeah, Three Blue One Brown channel. Now there you can look at the convolution. So he has a specific chapters on neural networks. Now there you can look at it. In which the queries will be resolved.
Yeah,
Okay.
sure, Chandan. I think maybe we can
Yeah.
continue with
Yeah.
the tutorial content.
So any other questions you have? Any others? So things are going on comfortably. No issues are there. Okay. So now with this, let's try to continue with today's discussion. Now today's discussion is basically around some of the topics that sir would have left in between for TS to fill in the some of the proofs and some of the algebra. Okay. Now in that manner, we will take some of the ideas from wherever he has left. I have listed some of the important points. I'm not going till the first session. I'm trying to finish off the things that he has recently done. So that your VAE and other stuff. So after VAE, he will go to the diffusion models. Now, once he goes to diffusion models, so you should be comfortable with those topics. So, what I thought is rather than going ahead with a lot of previous things that was there, there were some ideas on probability which, whenever type permits, we will come back. So, we will be looking into some of the stuff that Sir has left in VAE. Okay, so now the some of the basic proofs that I thought we will be covering today is one is KL divergence is always positive, and then the idea of law of the unconscious statistician. Now, depending on that, we will see whether we'll be able to go ahead with other ideas. Okay, just a minute. So now first we will take this weird thing that is law of the unconscious statistician. This is one of the very important ideas that you find in probability. Law of the unconscious statistician, also called as LOTUS. Not any party symbol, but just the abbreviation. Okay. So now it is used to calculate calculate expectation of a function of a random variable. Okay. Now g of x is a function of a random variable x. And then the assumption is distribution of x is known and g of x is unknown. If g of x is known, then you can directly get the density and then do the stuff, but it is not known. Let's say px. Now let this be PMF or PDF of x, depending on whether x is a discrete random variable or a continuous random variable. Now, what I'll be doing is I'll be going ahead with the continuous case. Proof for the continuous case is much simpler. So I'll be going ahead with the proof for the continuous case. Okay. Now let's say y is g of x. Okay. And then we assume some ideas on g. Now we say that g is differentiable and its inverse is
Chandan,
huh.
Chandan,
Yes, sir. Yes, sir.
sorry, I interrupted you. Pratosh
Yes, sir.
here. Yeah.
Yes, sir. Yes, sir. Got it. Yes,
Yeah,
sir.
I mean, if you can maybe just solve the midterm exam questions, no, that would I think be useful.
Oh, I myself did not prepare for it. Yeah.
So can we have a
No, it's
separate
okay.
tutorial for it this week, maybe for that?
Yeah, no
Huh.
problem. Maybe next week. Yeah, maybe next
Yes,
week.
sure, sir.
Or even
Yeah,
this week is
I-
fine. I think maybe I mean, going through the midterm is also something which we wanted to go through. So
sure.
good idea.
We will surely do it in the next session, sir. Yeah.
Chandan, one other thing, yeah, I'm sorry I'm
Yes, sir.
disturbing.
Yeah, no
Uh,
problem, sir. Yes, sir.
this Saturday, I will take the class between 8
Yes, sir.
a.m. and 11 a.m. Huh?
11. Yeah.
So,
I saw the message.
yeah, so you have the quiz at 11 o'clock, okay?
Sure,
After the
sure,
class.
sir. Sure. Yeah.
And,
Your son's interview is there.
oh, yeah, I mean, yeah.
Sir, all the best with the interview, sir.
See, the guy cannot talk. They want to interview him. I don't know. I mean, these Bangalore schools, right? I don't know what they are.
So they
Anyway,
will interview your son or you also. I mean, I
see,
don't
they've
know.
asked me. Otherwise, why would I go? No, I mean, my wife could have gone. So they have specifically asked both the parents to be present with the child. So you have to
And
go. I'll do that.
which
Chandan,
school
you
it
have
is?
the quiz at it's
11.
called Kumarans, one of the schools in the South Bangalore. Yeah. So
Kumarans
have
is
the
at the sixth cross, sir. DVG Road.
Tata Silk Farm. Yeah,
Tata Silk Farm. Yeah.
Yeah. So have that quiz on 11 o'clock. Okay, at 11
11.
o'clock.
Yeah.
And one
Sure.
other thing, somebody asked me to not have the quiz on 2nd of November, right? Because that's like a series of
Long
holidays and yeah, sort of Diwali, right? So what we can do now, 19th we will have a quiz, 26th we will have another quiz. Okay.
Sure, sir.
26th
Yes,
we'll
sir.
have another quiz. Maybe I'll discuss that in today. I mean, it's Saturday's lecture. I just wanted to let you know that one of these tutorials, no, you can see maybe, or you can do another thing. Why don't you just solve the midterm questions and just upload it in the group? You don't have to
Yeah,
spend time.
that I'll do. Yeah.
I think that would be
Yeah.
easier.
Sure. That I'll do,
And
sir.
we can
Yeah.
ask doubts if any. I mean,
Doubts if
anyway,
you
it
have.
would.
Yeah,
We
okay.
can ask the doubts if any. So it would be easier that way.
Yeah, sorry, Chandan, I disturbed you. Please
Hey,
continue.
no problem, sir. No problem. Yeah. Just
Sorry, Chandan.
give.
Before going
Go
into
ahead.
mathematics detail, can you just suggest what is the intuition why we are doing this law of unconscious guy?
I'll come to that. I'll exactly come to that. Okay.
Okay.
See, for example, I'll give you a very simple idea. To
It
calculate the
comes up in
variance.
reparameterization, no? It came up in
Yes.
reparameterization.
No. Reparameterization. So even a simple idea is to calculate the variance, you want expectation of x square. X square is a function of x. We know how to calculate the expectation of x. How to calculate the expectation of x square? We need the idea of LOTUS. That's the simplest example that we can think of.
Okay.
In addition to reparameterization, that's what Sir said. The simplest idea that
Good
we can
example,
think of
Chandan.
is, yeah.
Good example. I like it. Yeah. Good.
Thank you, sir. Yeah. So my internet got disconnected. Just give me 1 minute.
Sir, in between, what will be the syllabus for the next quiz? Will it be the last 2 classes?
Whatever has been covered till the previous quiz and see,
Okay.
we cannot compartmentalize things like that. For example, if I ask you a
Yeah.
simple question on probability, no, you cannot say that this is the quiz one's topics and then
Yeah,
we
yeah,
cannot leave
no
it, right?
problem.
Yeah.
But Chandan, don't ask things that I'm going to
No,
cover.
no, no,
Later.
no.
That is
No, 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 no,
unfair.
no, 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 no,
You
no,
can
no,
be
no,
Markovian. You should be ergodic.
no, 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 no. That I'll not do, sir. So now the idea is, the first of all, let's try to understand the name itself. So now it is called as law of the unconscious statistician. Okay. Now you will be able to understand why it is called such in some time. Okay. So it is not like simply they just use that name. Okay. Uh, it has a very deeper meaning to it. So the idea is you apply it in an totally in an unconscious unconscious way. Okay. What is this? What happened? Share screen. You're able to see my iPad screen? Okay. So now we know how to calculate the expectation of x. No, but now what we have is expectation. So we have a function of a random variable now for which we want to know how to calculate the expectation. Okay. So now let's try to understand how to do it. Okay. So now the conditions that we are imposing on G is now the function G that we have should be differentiable and the inverse should be monotonic. Okay. So under these assumptions, now once we have these assumptions, now the current code will work. I'll tell you how each of the conditions make sense. Okay. So now if y is g of x, then x is g inverse of y. Okay. So now what is d by dy of g inverse of y? What do you say about this? Can you compute this? Intuitively, can you think of the formula for this? Okay. So now this is, so just go ahead and refresh your calculus stuff. This is the inverse of y. Now this is This is by the inverse function rule. Okay. Now, that is nothing but this is dx equals 1 over g inverse of y dy. Okay. Now, all these things are fine. Now, where is this coming into picture? Okay. Let's write what is expectation of g of x. How do you write it? Now, this is continuous thing is what my assumption is. This is integral of y into fy of y dy. This is how I write it, right?
Chandan,
Okay.
sorry, it's g dash of g inverse of y, right? 1 by. I mean, we should take the differential of g. Right? Maybe I'm wrong. Sorry.
No, just go ahead. No, this is correct.
Okay.
Now, what is the distribution function of y? Now, this is probability that y is less than or equal to y. Correct? Now, this is nothing but probability that y is less than or equal to g of x. Correct? Now, this will be probability that x will be less than or equal to g inverse of y. Agree with me so far? Simple. So this is fx of g inverse of y. Now, I know the distribution function of y in terms of x. I know, see, what is my assumption? Now, let's go back to my assumption. Now, I am saying that distribution function of x is known. Now, because of this trick that I have used, I know the distribution function of y also now. Now, once I know the distribution, yeah, go ahead.
I have a question. So, when you invert the g, right, to the other side, x would be greater than g inverse of y, right?
A is less than b. 1 over a is greater than 1 over b.
Yeah.
1 over b is less than 1 over a.
Yeah.
Answers your question?
Yeah. I think I'll have to. I'll take a look.
Hey, no. There is nothing there. See,
yeah. So
okay.
g inverse of y is 1.
See, what is this? Is a. Okay, let's come back here. No, this is a. This is b. Correct. Apply this idea, you will get this. Exactly the same steps.
Okay.
No, inversion in terms of scalar is 1 by a, right?
Correct.
Exactly the same thing. See the inversion that is happening. No, b is coming here and a is coming here. You can see that?
Yeah. No, it's clear.
Okay. Now it's clear. Exactly the same idea.
Okay. Yeah.
Okay. Yeah.
Thanks, Chet.
Now, okay, whatever questions you have, you can stop me anytime. Okay. See, what will be happening is from most of the times these will be like more of a mathematical work rather than what do you call any intuition or any stuff working. Okay. Now this is basically most of the times our discussions will be more on a mathematical proof kind of ideas. Okay. So sometimes it is known that we will lose path. Now at that time we should take simple ideas like this to understand intuitively what is the steps that we are doing. Okay. So now finally, now I know the distribution function. Now if I know the distribution function, can I get the density function?
Yes, differentiated.
Differentiated, that's all. Fx of g inverse of y 1 by g of, make sense? Okay, so now let's go back to expectation of g of x. Okay, what is expectation of g of x? This is integral of y into fy of y dy, correct? Now this is nothing but what is y is g of x, correct? Y is g of x. What is fy of y? That is fx of g inverse of y into 1 by g into g inverse of y dy. What is g inverse of y? G inverse of y is x, and this is dx. This will be integral of g of x fx of x dx. Now this is expectation of g of x. This is the proof. See, what is this fellow saying? See, if you have a function, don't worry, apply this g of x on everything and then use the density of x only, which is mathematically crazy to us, right? No, but as it turns out, with these proof, it is very much clear to us, yeah, this is working. This makes sense? No, that is why it is called as unconscious statistician. You don't even have to be conscious. So just apply the function and take the density of x only, a density or mass of x only. Now it will work immediately. You don't need to worry about at all. Okay, that is why this fellow is called as law of the unconscious statistician. Make sense? Why it is called as law of the unconscious statistician? Good. I have done it in steps. Now to get this, I did this, okay? That's all, very simple. Any questions with this proof? I'm done it only for the continuous case. That too on a very restricted continuous case, where G is differentiable and inverse is monotonic. Okay, only for this specific case, I have considered it. Not for any other case.
Chandan, one question.
Go ahead.
How are we getting the derivative of G inverse of Y? Can you please elaborate a bit on this?
See, you okay? You remember inverse function rule? You know inverse function rule?
Maybe I'm missing out on that.
Okay. So now to do so, we should go on some more ideas.
That's the same as chain rule, Chandan, or?
No, it is basically the derivative of inverse. Okay, now how do you, okay, yes, it is chain rule. It is basically chain rule only. Now, how do you calculate? So, see, okay, 1 by x square. How do you do it?
x square inverse and then.
Correct. In the same way you proceed. Okay. Now it is basically d by dx of x to the power of -2. And how do you proceed? Tell me the full equation. How do you do it?
Minus
this
1
is
by
minus 2x to the
minus
-3.
2x minus 3.
Yeah. So fine. So always confusions will be there. You would have left all this differentiation integration some time ago, because of which, so we'll be rusty about the formulas, but that is fine. But the intuition is clear. Now does that answer your question? Whoever asked this?
Not completely. So if we are trying to relate inverse in terms of a reciprocal, then maybe I'm not able to understand that.
Okay.
I think Sanchit, you can just check for this chain rule, then you will get to know that how it works.
How do you do it? Okay. No, okay. This, rather than that, my previous example was much more simpler. D by dx of 1 over x square. How do you solve this?
So this is x to the power of -2. The rule
Correct.
will be d by dx of x to the power n, which is nxn minus 1. So in our case, n
Correct.
is -2. It will
If
be
you if you don't want to use that, is there any other way of doing it?
Yeah, it is. I think f of g of x, right? I mean, how do you evaluate
d
the
by
derivative
dx
of f of g of x?
f p by q.
Correct. So now, in a similar manner, you can obtain it for the previous case also. Okay.
Okay.
Make sense? Okay.
Okay.
Okay. Any other questions?
Chandan, one
next.
question. Why that monotonically increasing? I mean, where does that come into picture?
So that comes into picture in these steps. Okay. That is something that I have put it under rug. I have put it under rug. So now first you should understand what is monotonic sequence for that. Now, since we haven't discussed monotonic sequence and other stuff, so let's not go there. Okay.
I mean, is it coming from the definition of CDF that it should always be increasing monotonically, non-decreasing?
Yes. Yeah. It is non-decreasing. It is not increasing. Okay. CDF is monotonically non-increasing. Monotonically non-decreasing. Okay. Yeah. So it's like you have multiple layers of stuff. Okay. How much ever you peel, no, there will be something that is below it. Okay. Now we should somewhere put a stop. So now I'll always give this example. Now this example may be like, so there is something called as real analysis. Okay. What is 1 plus 1? 2, right? Very straightforward answer. But do you know the proof for 1 plus 1 is equal to 2 runs for 3 pages? There is a proper proof to say that 1 plus 1 is 2, which run for 3 pages. Okay. Now, at some point or the other, now we should stop it. Now, my point of discussion is like, at least at the top level, we should be able to understand the stuff and the derivations that we'll be looking in class and the tutorials. Okay. Yeah. Okay. So now the next idea that we'll be looking into is DKL is non-negative. Okay. So now to do this, now let's try to fix up some things. Now, let P and Q be the distribution function. Okay, let P and Q be the distribution function. Okay, and then they have density or mass. Now let's PQ be the density function respectively. Now, when I say these are two distribution functions, now the basic assumption is what is a random variable? Can you recall?
Function
X is from
function from omega to r.
Correct. Now, in these assumptions, P and Q, they have the same omega is the assumption. Okay, the underlying omega is same is the thing. Fine. Okay, so let small p and q be the density function. So how do you define DKL between two distributions? Let's say P and Q. How did you define this? This is integral of Px log Px by Qx dx. Correct? So now, if we are considering the discrete random variable, now then DKL between these two distributions P and Q, this will be summation over all x Px log of Px by Qx. Okay, fine. So now let's try to do it for the discrete case. Okay, let's prove for discrete case. So when I mean discrete, now what do I mean by discrete in this case?
The random variable is discrete.
The random variable is discrete. Okay, now please remember that both of them share the same sample space. Okay, now it is not like they have different sample space. If they have different sample space, you cannot even think of doing anything. Okay, so now what do we want to prove? We want to prove DKL is always greater than or equal to 0. Okay, so now need to prove DKL of PQ is always greater than or equal to 0. Okay, so now because of which I can write that minus DKL of PQ less than or equal to 0. Now minus DKL of PQ. Now by definition, this is minus summation of x P of x log Px by Qx. Now this is same as summation over x Px log Qx by Px. So far so good. Okay. So now we know that log is a concave function. What is a concave function? How does the log x graph look like? Is this a concave function?
Yes, sir.
Okay, what is a convex function then? Now, how to get the convex function from log x now? Do you know any ways of getting it?
Minus.
Okay, some good idea. Let me put that minus log x. Is this a convex function? How do you know that it is a convex function?
I think if you take any 2 points, then they are always above the curve. I mean, the line segment joining the 2 points is always above the curve.
The idea is called as epigraph. Okay, that is the next idea that we'll be discussing in the next tutorials. Okay, the idea is called as epigraph. We will come to that specific point in the next session. That's rightly correct. Okay, now log is a concave function, and then I invoke something that I haven't proved yet. We'll be proving it explicitly, and by there is something called as Jensen's inequality. There are so many of these inequalities. No, they are very much what do you call? Always there is something called as Jensen's inequality. Have you heard of any other inequality? No, not the inequality in the society, but in mathematics, have you heard of any other inequality?
Triangular inequality.
Yeah.
Triangular inequality. Apart from that, in probability, do you hear anything? There is something called as Chernoff bounds. Okay, there is idea called as Markov inequalities. So these things will come. They are very wonderful inequality to get the bounds. Okay, now we'll be discussing them in time. Now the Jensen's inequality basically says log of expectation of x is always less than expectation of log x. Okay. Now, what is this? Is this expectation of log x? Is that look like this form?
Yes.
Yes. Now this is maybe I did some mistake somewhere. Oh, there is a negative symbol, so I should be okay. Got it. Yeah. With me? Why did I take this symbol? Okay, there is a negative symbol here. Now, because of which I have taken the other inequality. Now, because of which I can cancel off this and this. Log of.
And then I have a query here. We said
Go ahead.
we said E log x is less than or equal to log ex, right? So in the previous example, it is not E log x, right? I mean, expectation is px. If it was px,
No,
p of
this
x
is
log
this
p
is
of x.
E log x. Okay, no, this is expectation of log x. Now, how do you get expectation of log x?
A summation of x into log x, right? That's what expectation of log x is, right?
For whom did you leave the density function? For me.
Okay. Yeah.
Okay, happens. Don't worry. All these things, we all of us will do these kinds of mistakes. Okay. Yeah.
Yeah.
Okay. So now,
Yeah.
what is this now? What is Q? Or to be even more specific, we are considering a discrete case. In discrete case, what is Q?
EMF.
Yeah. Now this is summation over all the x. What will be this?
1.
Now this is
This should be 1. Like log 1 is 0.
log 1 is 0, correct. See, okay, let this not confuse you. When I say again and again here, I'm just carry forwarding this. I'm not saying this quantity is less than this quantity. That is not what I mean. So if you are confusing with that, you can always write this. Okay. And I'm reusing the same inequality. So because of which, what I can say, dkl of q is always greater than 0. Hence the proof. Make sense? Okay. I have seen one mistake. Now, if px is a density function, can you define it clearly for me?
Probability that x equal
Correct.
to
So,
x.
so see, when you say fx of x, now you say that this is from R to 0, 1, right?
Yeah.
What is px? This is R to R. But if on the other term, if x is a discrete random variable, so then it is from R to 0, 1. Yeah. See the difference. That is the reason why your density is not a probability measure. This is not something that is coming out of because of this. If something has to be a probability measure, the outcome has to be between 0 and 1, right? And everything has to be positive. Now it takes real values. Okay. Make sense now? Okay. Yeah. So I thought I'll be starting with Jensen's inequality today. Yeah, we don't have much time. Yeah. Any questions? We will stop for the day.
Chandan, in the midsem, there was one question that whether DKL is symmetric or not. And if it is not symmetric, what are the consequences of that? So shall we cover this now or in the midsem review?
So what I'll do is I'll write the answers for everything. See, to be very frank, I haven't seen the midsem questions at all. Let me be very frank. Okay. No, I'm a very, what do you call, this, this will be there. No, so I haven't seen. I should start even. So we should come up with the answer script. Now, what I'll do is I'll come up with an key solutions, and then I'll put it out. And then in the next tutorials, that is next Wednesday, if you have got any questions, we'll surely take it up. Okay.
Yeah, that's fine.
Okay. Sorry, so if sir has told me, I would have looked into it. Even it did not come to me also. Sorry for that. Yeah. We will look it up in the next session.
Chandan, one more question.
Yeah. Go ahead. Go
Yeah,
ahead.
so this probability density function, right? So
Mhm.
that's a function from R to R you have mentioned. It's basically the if you differentiate the CDF, you get the probability density function, right?
Correct.
So
If x is a
yeah,
continuous random variable.
if X is a continuous random variable, so
Mm.
that can be looked at as a likelihood of the value taking X, right? X taking the value X. The
Why are you looking likely? Okay, fine. Then
would it go beyond 0 and 1 in so basically my question was like, yeah, would that value of px, the density function, go beyond 0
mm.
and 1
Yes. That
when
is
you
what
said
I'm
R
saying.
to R?
Yes.
Probably can
Yes.
you give an example that would
Take
help?
Gaussian distribution.
Okay.
Take any Gaussian. How is the density
Mhm.
of the Gaussian distribution is?
Yeah.
This is the density of the Gaussian distribution.
Hmm.
Okay. Now,
Hmm.
so if you make it sharper or larger, no, it will exceed 0, 1. You can do it easily. You can do it.
Yeah. So for example, even if you take a uniform distribution between 0
Yeah.
and half,
Huh.
and that can have a
It is
value
2.
2, right? At any
Correct. It
point
is 2.
between 0
Correct.
and half. Okay.
It is 2.
Okay. Got it. Yeah.
Yeah.
Thanks.
But it is not defined for a particular point, right? It has to be
Which one?
always, I mean, the density function, is it defined for any given point? We have to always take an interval, right? So we cannot evaluate
No.
PDF at a particular point, right?
No. What his question is correct. Your point is correct. What his question basically is, at any given point, what will be the value? You are correct. It will be 0 at a single point. Correct. But at any given interval also, it can take more than 0, 1 is my point.
Yeah, I think the question
Okay.
was like, I mean, how does it relate to the likelihood?
No, see, okay, don't bring in likelihood at all. Okay, so now it is much more simpler now without looking into likelihood, and then see it as an R to R function. Okay, now that will be
Yeah,
even
this
more
part is clear.
simpler. Okay, and it is much more simpler, and say that this is not a probability function. It is not probability. Your mass is a probability, your distribution function is a probability, but your density is not probability. Okay. Yeah. No questions? No further questions? Okay then. So meanwhile, maybe today or tomorrow at tomorrow or day after at max, I'll be putting the solutions for your quiz, sorry, for your test one online. So you can look at it, and then we will discuss any queries. So in the next tutorial session. Okay, and then we will continue with proving of this what do you call Jensen's inequality, and then we will continue with the discussions that are remaining. Okay, make sense? Okay then. So thank you. Let's meet next week.